Solving inverse elasticity simulations from camera observations is a hard problem. In this work, we propose a novel correspondence-free cost function based on sparse surface constraints. Our optimization process takes depth images from a single commodity RGB camera as input. A joint gradient-based optimizer then links the Lagrangian elasticity simulation with an Eulerian model of the depth observations. Our algorithm can successfully reconstruct plausible object motions. First, we will analyze the stability of the convergence on a synthetic example. Here, the ground truth simulation is shown with the simulated noisy observations. To evaluate the convergence, we sample 20 initial values for the Young's modulus. Shown here are the minimal and maximal values. In our first test, we compare the convergence when a different number of cameras is used. For 8 cameras, 19 out of 20 runs converge to the ground truth value of 5000. The convergence rate does not change when the number of cameras is reduced to 2 or even to 1 camera. Now the object is only seen from a single perspective. Next, we compare the convergence when different camera resolutions are used. For a resolution of 200 squared pixels, again 19 out of 20 runs converge. For 100 squared pixels, even all 20 out of 20 runs. And for a resolution of only 20 times 20 pixels, still 18 out of 20 runs succeed. Upon convergence, the reconstructed motion is indistinguishable from the ground truth. These tests show that our method achieves robust reconstructions even for very sparse data. Additional synthetic evaluations can be found in the supplemental videos. We will now test our method on real-world scans. In the first test, we let a teddy drop onto the table and optimize for the gravity, the Young's modulus, the mass damping, and the stiffness damping. Since the optimization is highly nonlinear, we sample 18 initial values for the parameters and choose the reconstruction with the lowest final cost. The best 5 runs are shown here. In the side-by-side comparison, one can see that the bouncing behavior of the teddy is close to the observation, even though the initial configuration is far off from the ground truth. In a second test, we let a pillow drop onto the table and optimize for the same parameters as before. We show the 2 best runs that are similar in the final cost. This demonstrates the strong nonlinearities that we have to overcome. The reconstructions are local optima averaged over all time steps. In a final test, we let a pillow drop on a ramp and additionally optimize for the orientation and height of the ramp. To our knowledge, this is the first attempt to simultaneously reconstruct material properties and boundary conditions from a single depth video. Again, we sample 20 initial values and show the best 5 runs. Note how different the initial states in the bottom row are from each other. In the side-by-side comparison, one can see that the optimization found a close approximation of the reconstructed material and position of the ramp. The remaining errors are due to our assumption of a homogeneous material and a non-frictional collision. Thank you for watching.